If someone asked you how much your luggage weighs, you would use a scale. But the Earth weighs almost 6 sextillion kilograms, a 6 followed by 24 zeros. Anyone can understand. This raises a deeper question. If weighing something requires lifting it against gravity, how do you weigh the very object responsible for the gravity in the first place? Isaac Newton recognized that apples, stones, and cannonballs fall toward the ground for the same reason. Every object with mass attracts every other object with a force dictated by their mass and the distance between them. Gravity behaves as a universal force, bridging mass and distance in a way that allows its effects to be captured in a mathematical blueprint. Newton's law of universal gravitation provides the mathematical framework for this attraction. Every part of the equation represents something observable. F is the gravitational force pulling objects together, m1 and m2 are their masses, and r is the distance between their centers. However, Newton never knew the value of g, the universal gravitational constant. Without this number, the equation only predicts relative behavior. It explains why planets orbit or why objects fall, but it cannot reveal the actual mass of the Earth. For more than a century after Newton published his theory, this missing constant remained one of science's greatest unknowns, preventing any calculation of the planet's absolute weight. In 1798, Henry Cavendish built an apparatus designed to measure this constant, a delicate brass torsion-balance. The instrument used a lightweight horizontal rod suspended by a thin wire, with small lead spheres at the ends. Cavendish placed much larger lead spheres nearby to exert a gravitational pull on the smaller ones. Cavendish measured gravity by watching the wire twist. The movement was almost imperceptible, sometimes moving only fractions of a millimeter. The suspension wire behaved like a spring, pushing back with a restoring force. By measuring how much the rod rotated and knowing the stiffness of the wire, Cavendish could calculate the incredibly weak gravitational force between the spheres. These measurements show that gravity is extraordinarily weak. A small refrigerator magnet can easily overcome the gravitational attraction of the entire Earth acting on a paperclip. Because Cavendish knew the masses, the separation, and the force in his lab, he could finally solve for the only remaining unknown, the constant g. Every object on the surface experiences a gravitational acceleration of approximately 9.81 meters per second squared, a value known as g. Newton's law predicts that the gravitational acceleration produced by a spherical body follows this specific relationship. Scientists can measure surface gravity directly, and Earth's radius is known from centuries of surveying. With Cavendish's constant now available, only one variable remains. Rearranging the equation isolates m, the mass of the Earth. When the measured values are inserted, the result is 5.972 times 10 to the 24th power, almost 6 sextillion kilograms. This planetary weight emerges naturally from local measurements made on the surface of the Earth. Determining this constant allowed scientists to calculate the masses of the other planets in the solar system. Spacecraft trajectories reveal how strongly gas giants like Jupiter pull on nearby moons and probes, allowing astronomers to calculate their mass through orbital motion. These same gravitational principles apply to Saturn and every other body in the system. The method extends further, allowing for the calculation of the mass of binary stars, entire galaxies, and the enormous masses of black holes. The same equation that describes a falling apple now measures objects spanning more than 40 orders of magnitude in mass. Despite its importance, g remains one of the least precisely known fundamental constants in physics. Gravity is so weak that modern laboratory measurements are often distorted by tiny environmental changes, such as temperature shifts or nearby vibrations. Astronomers often rely on the standard gravitational parameter, the product of g and m, which can be measured with high accuracy by observing orbital motion. The uncertainties in the gravitational constant only become an issue when scientists try to separate the mass from the constant itself. The Earth has never been placed on a physical scale. Instead, scientists learn to interpret the motions of falling objects, swinging pendulums, and orbiting satellites. By understanding the invisible force the planet exerts on everything around it, humanity discovered that the universe had already provided the scale.